Good morning, everyone. Today we are going to continue our talk about failure of materials. In our last class, we talked about brittle failure, and ductile failure, and we also have talked about the crack initiation, crack propagation, and the three modes of cracks. Mode 1, opening; mode 2, sliding; mode 3, tearing. And we also have talked about uh, we have talked about this impact testing, and today we're going to continue our talk. And here are today's objectives, which include um, we learn ductile to brittle transition of materials, and this is especially for metals and metal alloys. And then we are going to talk about fatigue. What is the fatigue? And then we talk about the creep. First, we talk about the impact testing in our last class, and I showed you guys we have two different impact testing, um, two types of impact testing. One is called IZORD, one is called this is the Charpy. We use the hammer here. This is the hammer. So this is the specimen. This is IZOD, just like I. Right? This is a letter, capital letter I. So this is a Charpy. It is placed horizontally. And so here is a hammer, and this is we break it. So this is a specimen. And if you have taken mechanical engineering lab with me or with other professors, or you will learn this. You would have learned this. You should know how this is impact testing is conducted and how to do the data analysis. If you are going to take mechanical engineering lab this semester, and I think today's lecture will be very helpful for you guys to prepare for this testing theoretically. And then we talk about the ductile to brittle transition. So here is the temperature. You can see the different at different temperatures, and the material has different impact energy. And we can see clearly that as the temperature increases and impact toughness, impact energy is increasing monotonically. You can both for this is the impact energy and also shear and fracture. And based on this figure, what conclusion we can get? We can get the following conclusions. The conclusion is if we lower the temperature, we are going to lower the ductility of the material. The ductility is kind of equivalent to impact energy or the toughness. That means it is much easier to be broken if we lower the operating temperature. So this picture shows the fracture stiffness of A36 steel. A36 steel. Okay, so A36 is a commonly used material in industry, and the Charpy V-chop the specimen, and V-chop for the Charpy V-chop specimen tested at indicated temperature, and so this is in degree C. Okay, so this is 59 degrees C is low, and the 79 is it is high, and usually 16 is the temperature. 16 to 24, they are the commonly used temperatures for industry in this for this material. As you can see, so this is the Charpy, the testing, and they have different appearance here. The ductile to brittle transition, the temperature we have we specify designate a temperature and to indicate that ductile to brittle transition. There is a ductile to brittle transition. So here is the temperature, here is the impact energy. So here is a low strength FCC and HCP metal for example, copper and nickel. So for this guy, it is as the temperature goes, as the temperature becomes higher, so impact energy does not change too much. So this is one case scenario. And second case scenario for high strength material, for example, if the yield strength is greater than the Young's modulus divided by 150, so this is called high strength steel and titanium alloys. So for this kind of material, and as the temperature increases and impact energy does not change too substantially. So this is case one and this is a case two, and they are very similar, and in that and the impact energy does not change as the temperature increases. However, another category, they have another category of materials. They have very substantially different impact energy at different temperatures. So here is, you can see it goes from here and it's jumping and so high to here. Okay, and this is a special kind of special category of materials. Usually they are low strength steels and BCC metals. For example, iron, when the temperature is lower than 914 degrees C, or is a polymer. So here is it is one point. Okay, so we select this midpoint and designate this midpoint as the ductile to brittle transition temperature. So to the left of this point, and so this material is very brittle, and to the right of this point, the material becomes more ductile. And I want you guys to know, for different temperature, the influence of for different materials. The temperature has different effect on their impact energy. Be very careful. So here is shows the effect of carbon content on the TRAPPI-V notch energy versus temperature behavior for steel. Here is the temperature, and here is impact energy. And so here is, this one is the different the carbon content concentration, carbon content. And so here is and you can see decreasing the average grain size resulting in lower of the transition temperature, and increasing the carbon content increase the strength of the steel and raise the CVN transition of steels. So this is the very important. Okay, so here is you can see increasing the carbon content increase the strength of the steel and raise the CVN transition of the steel. I showed you this picture, this slide in previous class, and today I'm going to show you again. So here is a pre-World War II, and so this is a tragedy, the Titanic. So this is the Titanic. We know, if you have ever watched this Titanic, the movie, you will know that. So here is a during the World War II, Liberty ships and also broke and in the frozen water, because the steels were used having the ductile to brittle transition temperature. The operating temperature is below that. This is a designated. This is the ductile to brittle transition temperature. If this is the case, so the material became very brittle, and if there is a decent level of impact, and so this is material can broke. So that is how and this is two shapes the broke in the this is a very cold this ocean water. And then we talk about the fatigue. So this fatigue, we know fatigue, right? Fatigue means that in last class we talk about this is crack propagation. So we talk about the fatigue here. Fatigue, we know fatigue means that you apply the load back and forth, back and forth. For example, compressive tensile, compressive tensile, compressive tensile. And as the time goes, even though the load level you apply is very, very low, much lower than the yield strength, and as the time goes, at some point, the specimen will be broken. So this is called fatigue. And fatigue, failure, and applied and cyclic stress. So here is the fatigue machining. So here is the barium. So here is the specimen, and here's the specimen here. Compression on top, and tension on the bottom. And this guy is rotating, and the flex coupling here. This is motor, and this is counter. I can count on how many cycles, after how many cycles. So this is material, this specimen, that breaks. The stress varies with time. The key parameters are, and this is the stress level, sigma m is the mean stress, and this is cycling, this is frequency. How frequent you apply. Sigma m is the mean stress. Mean stress is the half of the sum of sigma maximum plus sigma minimum. S is the stress level. This one. So key point, failure can cause part failure, specimen failure, even though sigma applied load is much lower than the yield strength, and responsible for about 90% of the mechanical engineering failure. So fatigue is very, very horrible, catastrophic. Okay, so also it happens without any warning, and be very, very careful. And whenever you want to design some components or the system, and you need to take care of the loading conditions, commonly used loading conditions, especially if you need to check if there are any possibilities that this is a component or machine is operating at periodically will experience periodic or repeated the loading. If this is the case, you need to conduct fatigue analysis. Otherwise, it's kind of dangerous. And here is the fatigue. So these are three different figures. And figure 1 is reverse stress. You can see go from 0, go maximum, and then go down to the minimum, maximum and the minimum, and they are positive. And so here is we also go there, but and this time, so this is 0. The sigma m is not equal to 0, and sigma m is positive here. And for the C is random stress cycle. And if you are taking computer-aided engineering class, and I'm going to teach you and how to predict this is a fatigue life of the specimen, and if the loading condition is given, and also loading condition is given, and also this material is given. So we talk about types of fatigue behavior, and here for this is iron containing the metals. Iron containing metals we call ferrous metal, right? So fatigue, and they usually have a very, very clear cut. So this is the endurance limit. And so this endurance limit, so here is just like very clear cut knee, and go this way, and so this is horizontal. So here is the number of cycles to failure, and here is the stress, and you apply. And if the stress level you apply is less than, this is the as fatigue, and it is denoted as fatigue here. And in computer-aided engineering or this machine design, we use the endurance limit to denote this line. So this value is called endurance limit. If the applied force is less than this endurance limit, theoretically, no matter how you apply the cyclic loading, and this specimen will not fail. But in practice, it will fail because the specimen has a lot of defects. Any questions regarding this slide? Okay, so as I said, for the ferrous materials that contain iron, and we have these kind of properties. However, for other materials, there is no fatigue limit, and so here you can see no fatigue limit. So this is no clear-cut knee, so there is no straight line here. So for no endurance limit. For example, aluminum. So this is a steel, and steel is iron-containing metal. So this is the so this one is very special for iron containing metals. And then we talk about the rate of fatigue crack growth. If we have a crack, already existing crack there, and then you apply the cyclic loading, and what the condition, and how long it takes, and for this crack tip and continue, and you can calculate the crack tip length, the crack propagation length. The crack grows incrementally. So this equation is a derivative of crack length with respect to number of cycles, and it equals delta K exponent M. Okay, delta K is, what is the K here? Last time I told you there is a concept in the context of fracture mechanics, and it is called stress intensity factor, which is clearly different from stress concentration factor, right? So here is delta K is the range of stress intensity factor. In last class, I taught you how to calculate a stress intensity factor if the geometry of the specimen is given, and if the loading condition is given, and how to calculate this K. Now, this delta K is a range of stress intensity factor. Why? There is a range because you apply the load that is a cyclic, which has maximum value and minimum value. And so as here, this delta K equals is proportional of here because there is another factor which is called geometry correction factor lambda, or called Y. For convenience here, we just list this is a proportional relationship. Delta sigma is the range of the stress and the square root, and this is A. A is crack length. M is the power of this equation, which typical value 1 to 6. And so this is M, also actually is a C here, okay? This is a C here. And C and M, and they are material properties, and they need to be determined using multiple experiments. Okay, so field rotating shaft. Here is the field rotating crack. Crack grew even though K maximum is much less than Kc. As I said, this is fatigue, right? This is fatigue. And the crack grows faster as delta sigma increases. This delta sigma increases, delta K will be increasing. Crack gets longer. If the crack is longer, loading frequency increases. So this is understandable. Any questions regarding this slide? And I might ask you guys, what is the meaning of this equation? What each of these letters stands for? So as I said, for this, actually there is a C value here, C value in front of these parentheses, and this capital C value, and this is lowercase m value. They are material parameters which are determined using experiments. So here is a crack origin, and then go there. This is sharp cracks. So how to improve this fatigue life? How to improve fatigue life? and there are several ways I'm going to show you guys. So first, impose compressive surface stress. If this is a specimen, if you can impose compressive residual stress, then you can improve the fatigue life. There's a method, short pinion. And you know short pinion, right? Short pinion means that there is a very, very tiny metal particles, and you just project these tiny metal particles on the surface of the specimen, and then because this projected, this is a tiny metal particles will compress the surface of the specimen, and they will generate compressive residual stress. Residual stress means that even though these particles finish impacting the surface, and the stress are still there, residual stress. You should know that compressive residual stress improves fatigue life. However, tensile residual stress facilitates the crack initiation and crack propagation. As a result, tensile residual stress is bad, is detrimental for service life, for the fatigue life of specimen. I want all you guys to write this down. Right? So this is first is a short pinion, and also this is a traditional short pinion. Also, one of my research areas is the laser shock pinion. And laser shock pinion, we use a laser beam to induce the residual, to induce this is compressive residual stress in order to improve fatigue life of specimen. I want you guys to write down. In addition to this short pinion, I also have laser shock pinion, and using the laser beam to generate compressive residual stress. So this is the pinion. We call this the pinion. And second one is carbon rising. Okay, so this carbon rising. Last time we talked about this case hardening, right? So this case hardening, carbon rising means that, and we can use this is case hardening. We put in the chamber, seal the chamber, and we put our specimen there, and then we put this is a carbon containing gas or liquid, and usually we use gas in the chamber also, and then we seal the chamber, close the door of the chamber, and then seal it, elevate the temperature, and then hold for a certain amount of time. And after that, during this process, the carbon atoms will come diffuse in the surface of this specimen. And so usually this kind of gas includes methane, CH4, methane. And so as a result, so this specimen surface will be hardened, and also we will have compressive residual stress on the surface, which can improve the fatigue life of the specimen. I want you guys to write this down and fully understand use your own words to describe the process of case hardening or the carbon rising process. Right? So this is very, very important. The second category is remove stress concentrators. And stress concentrators means that there is abrupt the change of the geometry. And for example, for this case scenario, this is bad. Why? Because there is no fillet here. So this is the geometric change, abrupt geometric change. So that's the result. Here, this corner, and we will have stress concentration factor. So this is the sharp angle serves as the stress concentrators. And however, if we have a fillet rounded, this is the corner, so this will be much better in terms of fatigue life of this specimen. Any questions regarding this slide? No question? And we talk about our next important concept, creep. Right? So this is a creep. And what is a creep? And also in the mechanics solids lab, we are going to do the creep testing. And creep means that at a certain temperature, if given a load, even the load remains constant, however, the strain keeps growing. And so this is called creep. Right? So this is at the very beginning, people found this phenomena when people took care of this is engine. No, this is engine, titanium engine at a very, very high temperature. And they found that even though the load did not change, but the strain continued changing. So this is the creep. This is a creep. And sample deformation at a constant stress versus time. You can see. And so here, primary creep. So here is the creep. Okay. So these are 3 stages. And the primary creep, secondary creep, and so this tertiary creep. So by the way, this figure is very, very similar to the figure for the fatigue life. We also have stage 1, stage 2, and stage 3. And stage 2 of fatigue life is called the Paris law. It's called Paul Paris founded this law, and this is called Paul Paris law. Okay, you should know that this figure is very, very similar to the figure showing the fatigue life. So this is primary, secondary, steady state, constant slope, and tertiary creep, slope creep increases with time, and acceleration of this is the acceleration of the rate. The creep is a temperature dependent, right? So you should know that. And creep usually occurs at elevated temperature, and when the operating temperature is about 0.4 of multiplied by this is the melting temperature. I'm in K. This is in absolute temperature K Kelvin. So you can see here this is the time. So here is a primary. Okay, so each of these curves has 3 stages: primary, secondary, and tertiary. And so here is elastic. Right, so here the creep strain. You can see it goes increasing temperature, and so we have different higher the creep strain. Questions so far? So secondary creep, this is a steady state creep. So here can be described using one equation. And strain rate is constant at a given the temperature and also the stress level. And strain hardening is balanced by recovery. And strain hardening is balanced by recovery. And we talk about hardening, and we also talk about recovery in our previous classes. And I would recommend you to fresh your memory about this is the strain hardening and recovery, and then you will have better understanding of the secondary creep. So this equation says that the strain rate creep strain rate it equals the K, this is K2, this is constant, and sigma n applied stress exponential exp the E function, and within the parentheses is negative. Don't forget this negative when you do calculations. The Q, this QC is activation energy for creep and material parameter. R and T, this T is operating temperature. R is a constant. And so here is the strain rate increases with increasing temperature and applied stress. So this is a steady state creep rate, and so this is a stress for different stress level. This is a stress megapascal. So for these 3 different temperatures. And so creep failure, how can I know this is a creep failure? Failure along grain boundaries, right? So you can see, so this creep occurs along the grain boundaries. So this is applied stress. This is specimen. If you have applied stress going this way, so these grain boundary cavities, and these cavities, and as the time goes, and these grain boundary cavities will grow bigger and bigger, and finally this is the breaks. The prediction of creep rupture lifetime. So here is iron temperature is given, applied stress is given, and time to rupture, and you calculate time to rupture. And so here, okay, so this is using this equation. This is temperature, 20 plus log TR, time to failure rupture equals L, the function of applied load. And then here, so here is this is based on this figure, right? So this value is 24. This is life 24, and here is given log TR. Calculate. This is the TR. So solution, time to rupture the TR. T is given operating temperature. L is function of applied load, and you just plug in, and you can calculate this TR based on this new load. And then we talk about the effect of processing on creep resistance. And previously we talked about the load, temperature, and load conditions, how temperature and load conditions affect this is a creep. But now talking about processing, how the processing affects the creep resistance. For this is three different specimens, and they are made of. So this one is conventional casting. Conventional casting, we can see. So this is the surface roughness is high. So this columnar grain. So this columnar grain means that you can see columnar, okay, columnar column. This grain has a column like these grains. This material have column like grains. So this is a single crystal, and the whole thing is a single crystal. And so this is polycrystalline, the turbine, the blade that was produced by conventional casting. And second one is sophisticated directional solidification technique, and I'm going to talk about this and how we get these columnar grains. And this way is a single crystal blade.